Welcome back to the Deep Dive, the place where we take complex source material, filter out the noise, and deliver the nuggets of knowledge you need to be genuinely well-informed. Today we are deep diving into the physics of resilience. Specifically, how systems can maintain order even as they start to fall apart. We're wading into the world of synchronization and complexity, focusing on a phenomenon that it just perfectly captures this tension between order and chaos. It's called the Chimera state.
Right.
Now, for those who might have, forgotten their coupled oscillator theory, Chimera state is this stunning pattern where you have regions that are perfectly synchronized. Coherent, right? Existing right next to regions that are completely desynchronized.
Incoherent.
All in the same space at the same time. And this isn't just some lab curiosity in physics.
No. These chimera states are thought to be pretty fundamental to how certain natural systems operate. I mean, take the human brain. The generation of these metastable chimera states, this constant quick switching between order and disorder, that's linked to our ability to learn and respond to things.
Or one of my absolute favorite biological examples, unihemispheric sleep.
Oh, yeah, in birds and dolphins.
Exactly. Some birds, marine mammals, they can essentially rest one half of their brain. The neurons there are synchronized, quiet, and at the same time, the other half stays desynchronized and alert, watching for predators.
It's the ultimate biological compromise.
It is. Order and chaos working together.
And our sources today are looking at a really generalized, very practical form of this state. They're called amplitude-mediated chimeras, or AMCs.
And what makes them different?
Well, they're studied using something called complex Ginzburg-Landau oscillators, CGL for short. And unlike simpler models that just track, say, the timing or the phase of an oscillation, CGL oscillators also track the amplitude, the strength, which means they're a much better model for real-world nonlinear systems.
Okay, so a complex, realistic system. What's the mission here? What's the core question?
The core question is really about aging. We're using this as a model to understand what happens when a physical or biological system goes through, age-related deterioration.
What happens if some components just stop working? They die,
Right.
or just cease to oscillate on their own.
Exactly. How robust is that critical balance of order and chaos, the AMC, when its very foundation starts to crumble?
So we're testing the limits of resilience.
That's the central question. We want to know how the global coupling, that connection that binds all the components together, how it interacts with these inactive parts, and what mechanism lets the whole state survive against, massive functional decline.
Okay, let's unpack the model setup first.
Yeah.
This is where we define what aging actually looks like in the simulation.
So we have a globally coupled system of these CGL oscillators.
And globally coupled just means every single oscillator talks to every other one.
Correct. Equally. It's a very tight community. Then we split that community into two groups.
The haves and the have-nots.
You could say that. The active population is where the internal parameters are set, so they naturally oscillate. They're healthy. The second population is the inactive one. And their parameters are set so that if they were left alone, they'd just settle down to zero.
They'd stop moving, functionally dead.
Exactly.
And you quantify this decline with its simple fraction, PL. So if PL is 0.1, 10% of the components are inactive.
That's it. And when P is 0, the system is perfectly healthy, and it shows the standard AMC state.
Which looks like what?
If you view it in the complex phase plane, it's very distinct. You have one tight cluster of perfectly synchronized, coherent oscillators.
The ordered part.
And then you have a kind of string, or maybe a cloud, of scattered, incoherent oscillators. That's your chaos.
The balance.
Yeah.
When you introduce that inactive population, even a tiny fraction, everything changes.
It changes fundamentally. Which brings us to the three main effects that the researchers observed.
And the first one is the one that really, it just seems to defy logic.
It is utterly counterintuitive.
We're calling it revival and structural modulation. You put in components designed to be dead, and the system just refuses to let them stay that way.
That is right. Because of the strong driving force from the global coupling, from all the other active oscillators, these inactive components, they experience a powerful revival.
They're shocked back to life.
They're forcibly jolted back into having oscillatory properties. They start moving again.
And this is the kicker, they don't just melt back into the original active group.
No, they can't. They're fundamentally different now because their internal parameters are still set to dead. So the coupling forces them to form their own separate, coherent cluster.
So if I look at a snapshot of the system, I'm now seeing two clusters.
Two clusters. The original, robust, active one, and a brand new secondary cluster made up entirely of the components that were supposed to be non-functional.
They've been revived and then organized.
Yes. And while this new group oscillates at the exact same collective frequency as the healthy group,
So they're marching in time.
they're marching in time, but they have a significantly smaller amplitude. They're oscillating, but just barely.
It's like they were forced back to work, but with drastically reduced energy. The whole structure of the Chimera state has been permanently changed by the act of survival.
It's a profound finding. The components that were meant to be passive to drag the system down are actually incorporated as an essential new part of the state.
Which makes you ask why. Why is it better for the system to do that, to incorporate them, instead of just letting them die off?
That's the million-dollar question. It seems the collective stability of the entire system depends on forcing them to comply.
It's an extreme form of systems management.
And that leads right into the second and third effects, which really show the cost of this forced revival.
Okay, so there's a price to pay.
There is. The second effect is that the overall presence of these inactive oscillators, it reduces the common collective frequency, omega dol.
Meaning the whole system slows down.
The more dead weight the system has to carry and revive, the slower the whole thing operates. As that fraction pull goes up, the system's collective oscillations slows down.
It survives, but it loses speed.
Right.
That feels like a perfect parallel for aging in, well, anything. Biological systems, mechanical systems. We keep the core function, but we pay a price in efficiency.
And the third cost is the impact on the system's comfort zone.
Its existence domain.
Exactly. That's the specific range of system parameters, things like nonlinearity and coupling strength, where the AMC state can even exist in the first place. As 2 increases, this entire domain shrinks a lot.
So the sweet spot for this balance of order and chaos becomes a tiny target.
A tiny target. And our sources show it also shifts upward, which means you need much higher coupling strength, a higher dollar, to maintain the state at all.
You need to pump more energy in to keep it stable.
You need more driving force to counteract the drag. But this all leads to the truly remarkable finding about the robustness of this state.
And this is the insight you, the listener, really need to take away from this. So what's the upper limit? How resilient is it?
The most surprising result is that these amplitude-mediated chimeras, they continue to exist even when the fraction of inactive oscillators, PFA, is as high as 0.9.
90%.
Yes.
Let that sink
Yeah.
in. 90% of the components in the system are functionally dead.
They're designed not to oscillate, but the global dynamics are so powerful, so stabilizing, that they reactivate that massive, overwhelmingly inactive population.
Force them into a new, slower ordered structure.
And the core balance of order and chaos persists.
So the system is essentially running on 10% functional power, but the coupling, the connection between the parts, is able to sustain this organized state across the other 90%.
That's it. This isn't just robust, it suggests the coupling itself is the true functional engine. It's way more important than the initial state of the individual parts.
The AMC state shows extraordinary resilience.
And that level of resilience, it demands an explanation. We can't just look at the simulation results, we need to understand the dynamics behind it.
Right, so we're moving from the what to the why.
To understand the origin, the team simplified the model. They used what's called a mean field approximation. So the full system, with hundreds of oscillators, is reduced mathematically to just 2 driven single oscillator equations.
One for the active population, one for the inactive.
Exactly. And the key to both of those simplified equations is the common mean field, $5.
And $5 is
What?
the aggregate voice of the whole system.
That's a perfect way to put it. It's the collective signal generated by the global coupling. And that signal is the driving force for both populations.
So this lets us trace the connection. We already know that as the inactive fraction t-tau goes up, the collective frequency omega goes down, it slows.
And the mean field amplitude, tradiol, also decreases.
So the sheer weight of the dead components weakens the collective signal and forces that slowdown.
Precisely. And by performing a bifurcation analysis on these simplified equations, we can understand why the domain shrinks.
How does that work?
The increase in Badhau causes shifts in other system parameters, which pushes the system out of the sweet spot needed for the AMC state. Imagine the state as a subtle dance in phase space. The AMC corresponds to a stable spiral.
Yeah.
When Badhau increases, the system is pushed toward instability. That stable spiral can collapse into a simpler fixed point, which we call a node.
Hold on, let's unpack that. A stable spiral collapsing into a node. What does that mean in plain English?
It means the complex structure that lets order and chaos coexist is just lost. When the spiral collapses to a node, the system snaps into a simple, predictable order. Coherence takes over completely.
So the Chimera state dies.
It's gone. Or, if the parameters shift the other way, you can hit a saddle node bifurcation line, and chaos takes over everything.
So the shrinking domain is just analytical proof that the conditions for this delicate state get much, much stricter as components fail.
Right. You need more collective power, that higher coupling dollars, to fight against the parameter shifts caused by the failing parts.
Okay, that explains the collapse and the shrinkage. But what about the revival? The dead coming back to life? How does an equation predict that?
It comes down to the fundamental geometry of the equation for the inactive population. When you analyze the topology of that simplified equation, you find it only admits one type of stable behavior when it's being driven by the mean field, $5.
And that stable behavior is oscillation.
Essentially, yes. The coupling forces it into periodic motion. The system's natural resting point when it's being driven is a stable oscillation, not settling to zero.
So that's the mechanism for the revival. The physics itself says the only stable way for a driven, inactive part to exist is to get in line and start moving.
They are forced to maintain order because that is the most stable state available to them under the collective pressure.
That's a beautiful self-repair mechanism built right into the dynamics. The system inherently resists collapse by forcing its damaged parts to contribute, even just a little.
And that's really the final insight here. These AMCs are a generalized class of chimera states that are highly relevant because they include amplitude variations and don't rely on restrictive coupling. They're robust, stable structures.
Which brings us back to the main insight for you, the listener. The structure of order and chaos, the AMC, is shockingly resilient. Even when 90% of the individual components are designed to fail, the global coupling is strong enough to reactivate them and pull them into a new, slower, but fundamentally ordered state.
The system isn't just tolerating damage, it's leveraging its interconnectedness to restore function in the damaged parts.
So if we believe that the collective dynamics of neurons in the brain rely on chimera states for learning, what might this robustness against a 90% loss imply about the brain's massive redundancy, its ability to maintain core functions, even with significant age-related damage?
We know biological systems slow down with age.
Right, but this research suggests that the collective synchrony might be the very last thing to go. What happens when a system is inherently designed to leverage its weak components to maintain synchrony? That is a thought that might change how you view everything from network redundancy to the very limits of biological aging.